So let's begin our look into our first of our Extension 2 topics, that being complex numbers, which, believe it or not, you've been working with all your life. Let me explain. Solving quadratics. We obviously know how to do this, and here's a very simple quadratic. X squared plus 1 equals 0. We probably moved the negative 1 to the other side, and up until now, you would have said no, well, possibly wouldn't have used the word real, but you would have said no solutions. The reality is there are solutions. There's just no real ones. Now, in maths, we don't let these sort of things stop us. Okay? Because all we do is invent a new number. And then, like, there's other functions. There's a classic one called the error function. Because there's this problem that comes down and you get to a point where it's like an error. So in order to do the problem, you define the answer to be the error function, which is the answer to this problem, which we can't solve. But then we can go on and do problems, because whilst I don't know the answer, I'll go and use this. Similar sort of thing here. You know the answer, so we'll make it up. So we define a new number. And that new number is, in fact, a letter. And that letter, of course, is I. I is equal to the square root of negative 1. Or more correctly, the more correct definition is I squared is negative 1. Right? Not I's the square root of negative 1, but I squared is negative 1. Okay? And I is what we call an imaginary number. So now we can go and solve our problem. We get x squared is negative 1, so it's plus or minus the square root of negative 1, so we get plus or minus I. Right. Now, all of our complex numbers can be written in the form x plus iy. And the most common letter we use is z. We sometimes use w. I mean, it's just a pronumeral at the end of the day. But you'll see z used a lot. And x plus iy. So let's define a few things. And what we say is every complex number has a real and imaginary part. And I said before that you've been dealing with complex numbers all your life. You have. You've been dealing with the ones where the imaginary part is equal to 0. And that's real numbers. Okay? But the imaginary part can, of course, have a value, and there's this whole host of other numbers that we haven't played with. So x in this one would stand for the real part, and y is the imaginary part. So if I have 3 plus 5i, very simple question, what's the real part, what's the imaginary part? The real part is 3, the imaginary part is 5. It is not 5i. The imaginary part is 5. The I, when we write the number down, is telling us this is the imaginary part. All right. If the real part is equal to 0, then we have a purely imaginary number. There is no real part to it at all. It's totally imaginary. So anything which is simply a multiple of I would be a pure imaginary number. And as I just said, if the imaginary part is equal to 0, that's what you've been dealing with all your lives. They are real numbers. Some example of real numbers. 3/4. Pi e minus 4. I could pick many more. In fact, I could pick an infinite number more. Now, every complex number has a complex conjugate. Reason for that is they are surds, because remember, I stands for the square root of minus 1. And surds have conjugates. So a complex number is actually a surd. And so its conjugate, though, is when the imaginary part changes sign. So x plus iy, its conjugate is x minus iy. So the surd part, or the imaginary part, changes sign. And you'll notice the symbol there that we use is a horizontal bar over the z. It stands for conjugate. So if z is equal to minus 2 minus the square root of 7i, then the conjugate, so z with the bar over the top, is minus 2 plus the square root of 7i. Okay, so this box, if you like, represents all the complex numbers, every number we possibly can imagine. And we break them up into what we've been working with, the real numbers. That's when y is equal to 0, there's no imaginary part. But now I'm saying is we also have this other set of numbers that we haven't been dealing with before now, where y is not equal to 0. Well, there's all these imaginary numbers in here. Now, our real numbers we know we can break down into rational numbers, which of course are numbers that can be written as a fraction, numbers that we do know the exact value to. And then there are irrational numbers. They're the ones that we don't know the exact value of. They're the ones that can't be written as a fraction, so pi being the classic example. So inside the rational numbers, we have fractions. I guess by fractions I'm meaning where the denominator is not 1. And then we have our integers. That's where the denominators are 1. Inside the integers, we have the natural numbers. And we have 0, which is just sits by itself, this very unusual number of 0. And of course, overlapping all these, we have the negatives. So you can have negative integers, negative fractions. You don't have negative 0. You don't have negative natural numbers. But you can have negative irrational numbers and so on.
What's a natural number?
Counting numbers. So 1, 2, 3, 4, 5. So. Now, over in our imaginary numbers, not quite as broken down. Pretty much we just have pure imaginary numbers as a special type of imaginary number, and they're the ones where x does equal 0. But that's pretty much it, okay? Because every complex number is a surd, if you like. So they're all sort of irrational, if you like. And so as they're irrational, we don't talk about fractions and integers and when we're talking about complex numbers. Anyway, the interesting thing about imaginary numbers is you can't order them. You can't say this one's bigger than this one. Can't do it because they're imaginary. But the main reason why is because you can't place them on the number line. You can only place real numbers on the number line. If I can place it on the number line, I can order it and say this one's bigger than this one. But I can't put an imaginary number on that line, so I can't say which one's bigger. All right, some basic operations, and of course you know how to do this already. Right? I is a surd, so all those operations that we did with surds, they're the operations we do with complex numbers. So addition. It's also just like algebra. We can think of I like a pronumeral because a pronumeral is an unknown. Imaginary number, square root of -1 is unknown. And we do it exactly like algebra. That turns out to be -4 minus I. So subtraction, again, just like algebra. 12 minus 5i. Multiplication becomes like a binomial product. Now here's where we've got to be careful. Because unlike a normal piece of algebra, as soon as I see I squared, well, I squared is defined to be -1. And so I would change that to +6. Now, it may well be in my head I'm changing it to +6, and you don't necessarily have to write that down. So this tidies up to be -26 plus 32i. Okay? I cubed, if you got I cubed, would be minus I to the power of 4, and you're back to 1. Now with division, which is what we call realising the denominator. Now realising the denominator is not where you look at the denominator and say, ooh, that's the denominator. That's not realising the denominator, okay? It's just like rationalising the denominator. When we did surds, we rationalised the denominator because we wanted the bottom of the fraction to become a rational number. Same idea, we want the bottom of the fraction to become a real number. How do we rationalise denominators? We multiply by the conjugate. That's exactly what we do with complex numbers. So I will multiply by its conjugate, -8 minus 2i. The bottom of the fraction then becomes the difference of two squares. But you'll notice on the bottom it actually has a plus sign because the difference of two squares is actually the sum of two squares because I squared is -1. So when I'm dealing with these imaginary numbers, that difference of two squares becomes the sum of two squares. So I get 64 plus 4 on the bottom. So be very careful with that. On the top, it's just our normal algebra. You'll notice I changed this straight into -6. It was actually minus 3i times minus 2i, which gave me plus 6i squared, but I squared is -1, so I had -6. And so we get minus 38 plus 16i on 68, But we tend to break it up into the real and imaginary part, so I write them as two fractions, and I obviously simplify the fraction as well. So minus 19 on 34 plus 8 on 34i. So some basic ideas about conjugates. Addition, it doesn't matter. If you wanted to find the conjugate of z1 plus z2, you could add them together, then find the conjugate. Or you could find the conjugates of the individual numbers, then add them together. The actual order you do that in doesn't matter. That's what this is basically saying. And same with multiplication. If you had to find the conjugate of a multiplication of two numbers, you could find the conjugate of each individual bit, then multiply. Or you could multiply first, then find the conjugate. And same with division. So all those operations, it does not matter which way around you do it. Multiply by its conjugate, that's what I was just saying, is the sum of two squares. Not just any two squares, it actually turns out to be the real part squared plus the imaginary part squared. And a quick way of finding the reciprocal is this then. Because you'll notice if I want to find the reciprocal of a complex number, what I could do is multiply top and bottom by the conjugate. Now why on earth do that? Because finding the conjugate of a number is very easy. So I can write that on the top. And on the bottom, it's just the sum of the two squares. And I can put that on the bottom straight away. So it is effectively the same as just multiplying by the conjugate of the bottom. Pardon? What did I say? Oh yeah, I'm in the product. So if I want to find the reciprocal of 4 minus 3i, I can say, oh well, that's 4 plus 3i on 25. And says my answer, 4 and 25 plus 3 and 25i. So the conjugate on the sum of two squares. Okay. All right, so with complex equations, it's just like surds. You know how when you solve surdic equations, you say the surd part equals the surd part, and the number by itself equals the number by itself? It's the same sort of idea. Because we've got real parts and imaginary parts, they can't mix. So when we're solving these equations, the real part must equal the real part, and the imaginary part must equal the imaginary part. So if I've got two complex numbers that are equal, a1 plus b1i and a2 plus b2i, then a1 must equal a2, the real part must equal the real part, and b1 must equal b2. The imaginary part equals the imaginary part. So in order to solve this equation, I got two options. I could divide both sides by 2 plus 3i, or I could expand the left-hand side out and create a couple of simultaneous equations. So I think that's what I'm going to do. So expanding the left-hand side out and then grouping the real part with the real part and the imaginary part with the imaginary part. So the real part is 2x minus 3y. That must equal 4. The imaginary part is 3x minus 2y. That must equal minus 2. So we now have two equations, two pronumerals, simultaneous equations. Solving that, we get x is minus 14 on 5. Subbing back in, y is minus 16 on 5. We could also have complex simultaneous equations. Now, don't get confused. I'm not saying w and z are real numbers. W and z are complex numbers. But what I'm saying is if we get 2 times this one plus I times this one, the answer is 3 plus 4i. So in this case, I and 2i are like coefficients. So it's still the same rules. We just want to make the coefficients the same and eliminate. So what did I do for this one? I made the coefficients of w the same. So I made them both 2i. So I multiplied the bottom one by 2. But again, still the same idea. I'm going to eliminate, so I'll subtract. And I've subtracted the top one from the bottom one. So 3z is 2 plus 5i. So z is actually the complex number 2/3 plus 5/3 I. And so to get w, I could substitute back in, Or I could create new simultaneous equations. Which way did I do it? I've subbed it back in. So we know z plus 2iw, or z's now 2/3 plus 5/3 I, is going to be 4 plus 3i. So 2iw becomes 10/3 plus 4/3 I. So w will be 10 on 6i plus 4 on 6. But the one thing about imaginary numbers is we never have the imaginary part in the denominator. So I always have to realise. Now, unlike surds, where surds it's okay to leave something, well, the classic one is 1 on root 2, when we say, what's the sign of 45? Oh, 1 on root 2. We don't worry about rationalising the denominator. But when it comes to imaginary numbers, we always realise the denominator. We never leave the imaginary part in the denominator. So this 10 on 6i, and it's a very easy one, because all I've got to do is multiply top and bottom by I, and that's going to get rid of it. And so it becomes minus, and then the 10 on 6 I've simplified as well, becomes minus 5/3 I. So there's our solution. Okay, and that is, of course, the exercises that I should have said on the last one.